Hello, and welcome to our 16th lecture in our series on Vertex Operator Algebras. Today, we will prove our first theorem. It's an algebraic analog for the Stone-von Neumann theorem, which essentially guarantees the uniqueness of the canonical commutation relations in systems described by quantum mechanics. It was originally proved for bounded linear operators acting on a Hilbert space, but today our context will be, of course, purely algebraic. That said, one important point that we haven't stressed much, but is implicit in today's discussion, is that Z-graded Heisenberg algebras should have finite dimensional subspaces of homogeneous dimension. Alright, let's get started with a quick review of the relevant technology. Heisenberg algebras are Lie algebras, whose center is equal to the commutator subalgebra. Additionally, that center is one-dimensional. We consider integer-graded algebras, which possess the triangular decomposition into positive, central, and negative abelian subspaces, each reflective of their own graded dimensionality. There are maximal abelian subalgebras, those things whose spectra, you might recall, we use in physics to label physical states in a given module, and of course we consider B+. Last time, we saw how B+ forms the foundation for a special kind of induced Heisenberg module. Today, we'll be formalizing that idea of a foundation a bit more using the physical language of a vacuum. Let H be a Heisenberg algebra and V be an H module. A vector in V is called a vacuum vector if it is annihilated by the entire H plus abelian subalgebra. The subspace of such vacuum vectors in V is called the vacuum of V and is typically denoted by capital omega. Modules can be unruly, as original attempts to prove the Stone-von Neumann theorem no doubt discovered. For our case, we need a statement of what constitutes a well-behaved H module. Following FLM, we define a sort of parametrized vacuum condition C sub k on a Heisenberg module V by the following requirements. First, the action of the basis element of the center, what we've been calling Z or Z, must act by scalar multiplication by k. Second, there must exist a positive integer n such that any subspace of V of homogeneous dimension greater than n is trivial. To think of modules that would violate these conditions, you can, for example, begin by considering the so-called coherent states in quantum mechanics. I'll drop some links on these wonderful beasts in the show notes. With the vacuum structure now defined, we are in a position to begin today's discussion. We begin with a pair of useful and descriptive lemmas. First, lemma 1. Any Z-graded H module V that satisfies the condition CK has a vacuum vector. Proof. Suppose V is such a module. Because V satisfies condition CK, it has that integer n, which represents the non-trivial homogeneous subspace of highest dimension. So, consider some vector V in that space V sub n. For any operator A from H+, the degree of A acting on V is necessarily greater than n, because all elements of H+ have positive graded dimension. Thus, A on V must belong to the trivial vector space, and therefore must vanish. So, V is a vacuum vector, and we're done. Next up, lemma 2. Again, let V be some H module that satisfies the condition C sub k. Then the vacuum of V is a B+ module, and in that capacity is completely reducible to one-dimensional subspaces. Proof. For this proof, it may help to review the constructions of last time, section 15. Okay, first, of course, the vacuum of V is non-trivial by lemma 1. Additionally, by the first requirement in the condition C sub k, the action of Z from H0 on any vacuum vector is necessarily scalar multiplication by k. By the nature of the vacuum, each vacuum vector is annihilated by the subspace H+. Thus, the one-dimensional subspace generated by any vacuum vector V is precisely the B+ module isomorphic to F, considered last time as the foundation for the induced module M of k. Since the B plus action on the vacuum amounts to scalar multiplication by either k or 0, the vacuum is reducible to the direct sum of one-dimensional subspaces for any particular choice of basis for the vacuum. And we're done. In what follows, it will be useful to define an index set for that basis, say capital gamma. Now we're ready to state today's theorem. Let V be a z-graded H module satisfying the condition C sub k. Then V is isomorphic as an H module to the H module induced by the vacuum of V, considered as a B plus module. Proof. Okay, first, of course, we have omega V is the vacuum of V. We studied induced modules in section 11 and saw the Poincaré-Berkoff-Witt theorem granted an inclusion map I, in this case from omega V, into the induced module. Of course, omega V, being a subspace of V, has a canonical inclusion into V itself, and let's just denote that by J. Note also that J is a B plus module map. By the universal mapping property of the induced module, there is a unique map phi such that this diagram commutes. And therefore, phi composed with I equals J. And since I and J are both injections, so too is phi. Now, to prove our theorem that the induced module is isomorphic to V, we now show that phi is a surjection, making it an isomorphism. To that end, we follow the logic of FLM. Suppose phi is not a surjection. We will prove by contradiction. Then the quotient module V modulo the image of phi is non-vanishing. And because V satisfied condition C sub k, its quotient will as well. Therefore, by lemma 1, the quotient submodule must have a vacuum vector, rendering its vacuum non-zero. Suppose W is such a vacuum vector. So any operator A in H plus annihilates W in the quotient module. So let's let little v be a representative of the quotient in its parent module V. So little v is not in the image of phi. Moreover, any operator A on V equals 0 modulo the image of phi. And therefore, and this is the important step here, A on V is in the image of phi. Okay, so here's where things get a little technical. If we can find some vector t in the image of phi, such that the action of basis elements ai from H plus on t equals the action of those elements on V, we can form the linear combination in V, t minus V, which again is not in the image of phi. T minus V is, by construction, annihilated by all operators A in H plus, and is therefore a vacuum vector of V, which is not in the vacuum of V, i.e. omega V. This is a contradiction, which, if true, therefore implies our assumption is false and phi must be surjective. Did you get that? We are proving surjectivity by contradiction, by manifestly constructing a vacuum vector that cannot exist. Okay, so let's build that vector t which sits in the image of phi. By lemma 2, the vacuum of V is reducible to one-dimensional B plus submodules, each isomorphic to the field F. Therefore, the induced module can be represented as a direct sum of submodules isomorphic to M of k, the irreducible modules discussed last time. As above, let capital gamma index the vacuum omega V, and let little omega sub gamma be basis vectors for the vacuum. Let little v be a representative vacuum vector as before, and let A be some operator in H+, which of course has the basis vectors ai. Let's denote the symbols S sub I gamma as the component of ai on V in the induced module over the vacuum component F omega gamma. So S sub I gamma is parametrized by the homogeneous dimension of V and the basis of the vacuum of V. Because of the vacuum condition C sub k on V, we know that there is a maximum value of I, say I naught, for which S sub I gamma is non-vanishing. Now, V might be a wild and crazy direct sum of who knows how many copies of H modules, but it's fair to say that since the dimension of any subspace of H of fixed homogeneous dimension is finite, there is a finite subset of gammas such that S sub I gamma is non-vanishing. In other words, there are a finite number of S sub I gammas to contend with here. Let's take the isomorphism of M of k with the symmetric algebra of H minus, represented by polynomials in the basis vectors that we have been calling B sub j. As discussed last time, in this representation, the basis of operators AI act as derivatives on the factors B sub I. Thus, for each of the finite number of S I sub gammas, we have a simple inhomogeneous linear partial differential equation for some S k ds by dbi equals Si gamma, which, of course, has a set of solutions. Call those solutions T sub gamma. Therefore, T, the T we are interested in, equals the sum of those T sub gammas, and we're done. Finally, a quick interpretation of this theorem. Last time, we saw that M of k was an irreducible H module, which we now see has a one-dimensional vacuum. Therefore, any H module V is reducible to copies of M of k, the precise definition hinging upon the choice of basis for the vacuum of V. And that's our show. Next time, we'll look at two quick examples of H modules that will prove useful in our discussion of vertex operator algebras.